Hello.
Hello, how are you?
Hi. Great. Yeah, a little bit tired. I'm at Eat Denver now, so it's morning, but yeah.
Oh yeah. Well, you just said that you'd be presenting the stuff at it then. So like, is it today or some other day?
It's on Thursday, so I presented also. So there was Eat Border last week, and I also did the presentation on Saturday, and and yes, I will also present. There's this EF day on Thursday at Eat Denver, so yeah, I will also do a
Oh,
talk
that's
there.
pretty
So
great.
yeah,
Yeah. Like,
yeah.
did you get any feedback from the devs, like let's say the wallet devs or the dApps devs? So how do they feel about this thing? So were you able to get something like that from them?
So right now it's mostly the core developers who are really paying attention to this because like it's like fairly technical. So like I think uh I maybe at Denver maybe there will be more people. So at Boulder, it's a really small conference. So it was like a room of I don't know 30 people, maybe 40, and also from various areas. And yeah, so it would be great to hear from someone from the like user side, but it's still like so this is the EIP, and it's not even the API specification. So I think maybe at this point it's uh, harder for them to approach, but yeah, at certain point it would be nice to get their attention too. But yeah, so right now I'm mostly
Yeah, I mean,
discussing
getting
this thing with like core devs because yeah, I just want to get the EIP in. Oh, Kev is also here. Hi. It's great that you could come.
Oh, hey Joe.
So, hello. All right. So, I think yeah, now it's 5 minutes past four, so maybe we can even uh start and yeah, maybe someone else will join in later, but I think we can start this now. So by the way, Kev, you weren't here at the previous one 2 weeks ago, right? uh
Yeah, exactly.
just because of the context. Yeah, yeah. Okay, so okay, just then I want to do like a really quick recap of what, yeah, just to give some context. So first I will turn on screen share and set desktop one. Okay, so you should be able to see my screen now. So yeah, I will just use my Eat Border slides now. So can you see my screen?
Yeah.
All right. So so this this there's this latest design, this 7745B, which maybe will get a separate EIP number at a certain point, but not yet. Anyway, so this is currently probably the best approach. But and let me just quickly show what it's about. So basically, uh there are these so the way it works, let's maybe I will go for this figure first. So it generates search tables, and yeah, we can go I will go into how they work exactly, but right now it's not even very important. So the interesting thing is that so this latest version of the log index, it the way it works is that it generates so-called index tables, and index tables contain the events of like either a single block or a certain number of blocks, and and the way they are generated is that uh, with the head block, with the currently processed block, a new index table, single block index table is generated, and uh, and later these tables are merged together into bigger tables so that they are form like a bigger search tree that is more efficient. And so the thing is that only so there's a single block table that's generated like during block processing like synchronously, and then uh, later bigger tables. So in this design we merged like four single block tables into like this second row from the bottom. These tables are represent like four blocks, and then there's another uh, chain of tables that is each table represents 16 blocks and then 64 blocks. And so these higher level tables, they are generated asynchronously, so they can be processed when there's no block processing happening, and probably this is the smallest amount of burden we can put on the protocol. And so this is how this index is generated, like from a high level overview in the consensus. And yeah, so the way let me just quickly. So this is one of the tables. This is how it looks, and what it has is basically it's an ordered list of the events, and it's tree hashed. So it can be the events of single block, or in this case, this is the events of multiple blocks, and they are ordered by content first and then inclusion position. So there's also an example of how we use it for proofs. Like the simplest example is like an exclusion proof. So for example, if we want to look up an entry, which is in this example a non-existent transaction hash, then uh, we look into this table, which is either we can do a binary search, or if it's locally stored more efficiently, it can be a more efficient search tree. Anyway, so we look up the position where this entry should be if it's present. And then if we find it's not present, like in this case, then we do a Merkle proof that proves the entries before and after the non-existent event. So and we know that this list is ordered, so this proves that this event doesn't exist. Or I have another example, yeah, which is a bit more complex because it's a log pattern search, and yeah, I don't want to spend a lot of time with this now, but uh, for example, here at the bottom there's this four red lines. These are the proven entries. And for example, if we want to prove all the instances where there's this topic one equals a certain uh, value, like this is a sender address of a USDT transfer, and the sender is called Bob, and we find the two occurrences of this uh, topic, and then so the proof also goes similarly. So we prove the actual matches occurrences, and we prove the two adjacent entries in order to prove that there's no more matches. So this is how these tables work, and I already implemented these tables in Go Ethereum, and they are super fast to search, and yeah, so uh, this could be very nice. But the thing is that there's a reason. So in this drawing, this is what I would want to put in the protocol. So in the block headers, basically I would hash in a chain of single block tables, four block tables, and up to 64 block tables, but not bigger ones, because with this design, it's guaranteed that the block builders and validators only need the last 80 few blocks to generate or verify new blocks. So it's manageable, but I don't want all the so that would be a too high demand on every participant of the protocol for them to process tables of, I don't know, hundreds of thousands of blocks. And yeah, so bigger tables than 64 blocks should be somehow proven off chain. And so that's the basic idea, and that's why I want to use ZK proofs now. And yeah, so there's this. I even made like one of the slides where I just explained why I want to use both in protocol processing and ZK proofs, but I think it's like kind of obvious. But so with the latest blocks, it's very good to process the things in protocol because otherwise anything between the latest generated ZK proof and the current head, and all the search would be unindexed, and unindexed search is extremely expensive. And so yeah, it's I think this could be a really good balance to just like do a little bit of processing in protocol and basically use the same data structures, just prove them with ZK proofs uh, for like bigger tables. And in the end, we would have kind of yeah. So this drawing shows like, so this is how this index tables would cover the whole chain history. So we would have like small tables, bigger tables, and for the order history, even bigger tables. And we could basically cover the entire chain history with a logarithmic number of tables. So an inclusion or exclusion proof of an event or combination of events, that would be roughly log squared, because there's a logarithmic number of tables, and the Merkle proof in a table is also logarithmic. And I calculated that with a current mainnet data, a full history lookup for a single event would be something like 40 kilobytes, which is very good. It's just so the only uh, question that we still have to figure out is whether we can really prove these tables with ZK proofs. And this is where I will certainly need some help, but I tried to already kind of imagine how this would work. And let me just open. Now, these are not really good slides. This is just some drawings I did for today. And yeah, zoom header just anyway, yeah. So wait. Yeah, okay. This is the right one. So basically, uh this first drawing here, these these numbered little boxes, these are like simplified representations of the index entries. So the index entries, they have like multiple fields, but still they are basically 64 byte uh binary entries, and they are ordered lexicographically. So like for simplification, now I just use two-digit numbers, but 64 byte entries can be ordered the same way. So this is how uh, merging two tables works. So these numbers are the same here and here, and at the bottom row they are merged into single single table. And what I want to achieve is that so these tables can be very large after time. So I think right now we have something. So mainnet has something like 20 something billion entries, and these don't all have to go into a single table, but at the like the order history would certainly be built of like billions of entries. So probably this is not provable with a single execution trace. That would be too expensive. So I wanted to design this thing in a way that that even a single table can be proven recursively, slice by slice. And so this is what this example is tries to show. So uh, basically, the way I want to generate a proof is, so locally the prover can generate the tables. So it already does have the smaller tables that it's merging together, and it already has the bigger table, and it can already calculate the table root. It just wants to prove that it's the correct table root. And and in this example, these green boxes, this is the section that the prover wants to prove that it is correct. So basically for this, what it needs is to prove the from the target table, it has to prove this section of entries with a Merkle proof. So that would be a witness for the private input of the ZK proof. And it also has to prove the corresponding parts from the two merged tables, smaller tables that are being merged. And also, like in this example, like this first entry is 33. So in the left small table, we do have the 33 entry, but in the other one, uh, we also have to prove like one entry before that in order to prove that before 36 there's no 34 or something like that. And also at the end, like the last entry we want to prove is 48, and in the left smaller table, like upper left table, we also have to prove the next entry. But basically, we only need to prove at most one extra entry at the each end of the proven section. So basically, we have to provide a Merkle proof of the merged sections, and that's so that's how we would prove a single slice. And but also we somehow have to like recursively merge these things together and not just single tables. So like this is kind of similar to what I drew on my presentation slides. So in this case, uh, we have so in this drawing, the smallest tables, these little blue rectangles are the 64 block tables that are generated in protocol. And basically we want to merge these further together. So somehow I would like to construct a proof in a way that so for example, once we have like this, so this proof somehow already proves that these are we have this 128 block tables and 256 block tables and so on, and these are all basically chain hashed together, so they can be proven. So this would be pretty much a similar structure than what the consensus has. It's just So this would be the public part of the proof that the proof actually proves that and the reason the bottom tables are different, they are called the reference table chain. That's why they are blue. Is that in every proof, so this would be the assumption, and the proof would prove that if these tables have the certain hash, which we can verify from consensus, then the bigger tables are this and this and this, the merged version of the same thing. So this is how it would look. And also, like this would be a partial proof. So when we are merging a bigger table, then we should somehow be able to also represent when. So in this case, the reference table chain would be probably
Sorry,
even
Bill.
like yes,
Sorry, I think I missed something on the previous slide.
yes.
So yeah, the second and third row. So the block count is 0x200, and the last block is 0xFFF. And the block count is 0x800, and the last block was 0xFFF. I don't understand why we have these two.
Okay. Oh yeah. Yeah, I wrote that those for a reason, so maybe I should also explain those. So in this case, so we should also store in the proof that what is the last block. And so basically the block count is, I used hex so that, yeah, it's just easier to see how it doubles and everything. But uh yeah, yeah, I messed up one of the block counts. So in the second row, the block counts should be 0x400. But anyway, so it should double from like 40, 80, 100, 200, 400, 800 as we go upwards. So yeah, they are like always double in size. And well, the last block is now it. I mean, the whole indexing starts at a certain block, probably like when like the EIP that generates the 64 block tables gets activated, then we can just call that. So that's where the indexing with EIP 7708, which also generates the logs for ETH transfers and everything. So yeah, so that's going to be a whole other story. And for simplicity, uh, in this case, we only care about like the post EIP activation chain, and but here I just assume that the indexing starts at block 0. So for example, like yeah, at the highest table, which is the block count is 800, so it starts from 0. Then the last block is 7FF logically, and also in below that, yeah, the block count should be 400 in the second row, and 4 times 400 is 1000. But yeah, so the last block is 1000 minus 1, so FFF. And yeah, this is just to so that so and in the consensus there's so in the protocol for those 4 table chains, uh, we always exactly know which is the last one, because there are protocol rules to when to add the new table hashes to each chain. But in case of like this higher tables and ZK proofs, uh, we should be a bit more flexible, because yeah, all of this happens asynchronously. So yeah, we should just store it also in the proven data structure. What is the last block? And also, yeah, also just probably store the block count too, because yeah, we we should not set it in stone how many chains we should have. It we could be adaptive. And yeah, anyway, so this is why we have block count and last block for every chain of index tables. Yeah. So the way these new tables would be constructed. So this is this last slide. So first we would start to merge together 2 tables. So one of them is like, I just switch back. So this is the second row. These 4 times 400 block tables, and here they are the blue ones because they are used as reference, because the 800 block table is being merged from 2 400 block tables, and only a certain section is being merged. But so this is something that also has to be represented in the proof. And and in this case, I don't want to enforce to prove the entire state of the other table chains, because recursively verifying an existing proof also has a significant cost. So why? So it's probably better to not start with merging it into every small proof, every partial proof, but first do these partial proofs, merge them together, and when we have a full table, then we can uh, merge them to the big thing. But I want to. So this example, I just wanted to show that the data structure can be so the way I specified it, and I will also show like some draft of the specification soon. So this is like it can store any number of full tables, and also like it can also uh, prove partially proven tables, and they can be merged in any combination. Even uh, multiple sets of full table chains can be merged together. If in one proof one table chain is proven further, and in another proof another table chain is proven further, and this is because this proof, so generating these proofs for the large blocks, this will be probably big effort for one prover, but for many provers. So I wanted to actually what I wanted to achieve is that even it, the work all these works can be merged together even if we don't have absolutely perfect coordination. So yeah, uh, and and this is pretty much what I want to achieve. And also the way I started to specify this, I really did. So this is really just should be considered a draft, but here it is. So I just started to write these type definitions and verifier functions in Go because yeah, I'm familiar with Go. Probably I will have to rewrite this in Rust. Uh, or yeah, probably Rust, I guess. But the way I imagine this, so this is like in my table proof branch in core log index table proof.go. It doesn't really do anything. This is really just some Go code shaped specification. So the table proof would be consist of a public and a private part, and so the public part, the thing that is being proven, is a set of or list of table chains, and the table chains are represented by the head. So as I shown on the drawing, block count, last block, and the head hash. So these table chains are hashed in a way that each table has a table root, which is the Merkle root of that list of entries, and the tables are chain hashed. So the previous head hash is hashed together with the new table root, and that's the new table chain head hash. So yeah, that's how I imagine this. And so yeah, we do have a list of completely rendered and proven tables, and we can also we can also include partial tables. Yeah, in this table chains list, the first one is always the reference, so that's also a rule because can only merge upwards. So yeah, it's obvious, and we always need one reference. So table chain 0 is always the reference, and even if we are just merging partial tables, we do have like the one reference chain, and the partial tables are yeah, they also have block count and last block, and they already have the table root because the prover already knows the table root in advance. It's like partially proven. It also yeah has the full entry count of the table, and these proven ranges, this range set, it's basically a subset of 0 to entry count -1. It can be like a continuous range or multiple continuous ranges, but yeah, it's just a subset of the proven entries of the table. So this is basically what I want to prove, and then this is the private part, like the witness is how we prove it. So they would contain optionally they could contain recursive proofs, which would be the same type of proof, just the proven stuff is being merged together. Uh, well, there's this table root proofs. That's just a technical thing. So because the public part only proves the chain head, and for example, for merging together the multiple tables, we do need the individual last few individual table roots. So these table root proofs can prove the last few table roots of any of the table chains. And there's the merge proofs, which is the actual thing of actual merging of table sections. And yeah, let me just scroll down a bit. So yeah, the entry is just defined as a 64 bytes. So here in this Merkle proof, we really don't need to care about the internal structure of the entries because they are just simple lexicographical ordering. And where's the merge proof? Yeah, table merge proof. Yeah, here's it. Oh yeah. So yeah, the table merge proof is is consists of table range proofs, and the table range proof is yeah, basically uh, there's the entry count and the first entry and the number of entries fully stored, and the left and right side Merkle branches. So yeah, this can be verified against the table root. And yeah, we for the merge proofs we have multiples, ones for the input, the smaller tables being merged, and one for the output that is being proven. And yeah, so this is pretty much there's also some code of how it works, and I don't really want to just go into those now. I even have to work a little bit on documenting those, but yeah. So this is my idea of how this proof would work, and now I will just need some input on whether this whole idea is workable. Could the proofs be implemented in this way, or am I just thinking something completely wrong? So
Um, sorry. Yeah, so I might need a bit more time to catch up on the general log index structure to see if anything's fully changed from when I last looked at it. But from the ZK part, the proof that you mentioned, I think it all makes sense. The recursive proof part, hmm, yeah, I guess it's unclear if you do need it, to be honest. Depends on how big the input is, because ZKVMs also do a sort of recursive proof internally. If the thing being proven is like too big, it will like break it up internally.
okay,
So
so
it's
how much is too big? Like for example, if the inputs are like, let's assume at most like it could be like 100 gigabytes. So that's probably too big for a single proof.
right, right. Yeah, I mean, too big here just means how much your hardware can handle essentially. Because the circuit for ZKVMs has like a limit, let's just say 100 million cycles. So you can always break down your proof into like chunks of 100. Sorry, you can always break down your program into chunks of 100 million cycles. And it's just on can the hardware do it and can the hardware do it in a reasonable amount of time. Um, so I think it depends. There might be other memory limits that I can't remember for like certain ZKVMs, but I think in general it's unclear if you do need the recursive proof part. Um,
Well, so one reason I might need the recursive proof is
mhm,
that even if it could, so maybe for most of the tables, proving one table maybe it could be done in a single proof. But the thing is that we have like this. Let's just yeah. Come back. So in the end, this is what I want to achieve. I want to, so I don't want like 30 proofs for all the different chains. So there's going to be like lots of these chains, and they will all keep changing. And I don't want to redo all the work, like reprove everything every time. So every time I will just want to do a proof of merging two head tables into a bigger one and two head tables into a bigger one at a higher level
mhm,
and I want to aggregate this knowledge. So that's the way I understand it. So that's done with recursive proofs.
mhm. Yeah, exactly. Yeah, I mean, if that's the constraint that you have, then I think the recursive proof approach works.
Yeah, by
And
the way, is there any difficulty with the recursive proof? So is it like an extra thing that needs some special tools, or I don't know.
not really. Some teams have implemented it. I'm not sure if every team has implemented it and gives you an API for it, because you need recursive proofs, but you also need to be able to access it in the Rust or Go program as well. Like you need to have like a verify proof method. Um, and I'm not super sure that everyone exposes it. Everyone roughly has it because of the idea I talked about where you need to like chunk the program into like 100 million cycles. But this is an internal thing. So I think yeah, the only downside might be that not everyone has it. Um, or sorry, not everyone exposes it. But
Hmm?
yeah, I'm trying to think who doesn't. Hmm. Mm, yeah, let me get back to you. I'd have to double check.
Okay, yeah. This is not something I expect to you to answer right now, but so I'm just wanted to present that
Hmm.
this is my problem, and this is what I will need some help with. And yeah, so or actually, you already sent me this example of the succinct demo, and I did like try that and ran the demo, and yeah, it looked really cool that it can uh, prove the like Fibonacci numbers. And I also tried to understand a little bit the other examples, and I even there I saw some recursive proof examples. So I'm not sure which tool chain and which technology would you recommend right now? Or this is also something that is like depends. So
Right. Yeah, for ZK VM, at least optional proofs or EIP 8025, we have like a framework that we've applied on top of the ZK VMs, which means that you can sort of abstract away each ZK VM that you're dealing with. Um, so I can paste the link to that here. In that sense, I think all of the technologies probably work as good. The only issue that you'd probably have is that most of them work with like low-level languages, so Go might not be a feasible a feasible language to.
yeah, it's not such a big problem. So right now I kind of implemented this thing, and maybe I need to polish a little bit, but the whole thing is like for with comments and everything, 400 something lines of pure code. So it shouldn't be very hard to implement it in any language. So that's not really a big constraint.
Okay, cool. So just pasting it in the chat. So this is what we use. Just pasted it in the
Mm-hmm.
chat. And this
Yeah,
just
yeah,
allows
it's
us to
east.
abstract away.
Mm-hmm.
Yeah, so yeah, I mean, yeah, I don't suggest any particular tool chain at the moment if you're like still experimenting and trying to check what works. I'd probably suggest to use this, or if you're familiar with Succinct already, then maybe just continue using that. And then once you want to productionize it, we can abstract away the succinct particular details.
Yeah,
Um,
actually, I'm not super familiar. I just yeah try the demo and try to just understand what I really need to
mhm.
do. But yeah, so by the way, so this is another thing I wanted to ask is so this that some one thing what I understood from Succinct was that it can generate like like big proof stars which are like around a megabyte or something. So they are kind of big, and for if you want to if I want to verify these proofs on chain, which I don't necessarily want to do, maybe the proofs can just be transmitted to the clients and they can verify it themselves. So these proofs, I'm not sure if it's worth verifying them on chain, but there's an alternative, some other proof system which is probably Snark, if I understood correctly, which is like really small, like hundreds of bytes. So what is the main difference between these? Is it like quantum security, or why are they're like very large and smaller proof systems?
Mhm. Sorry. So yeah, as you notice, there's like a Stark proving system and a Snark one. The Stark one basically has a log. It scales logarithmically in the complexity of the thing you're proving, roughly. So it's about 1 MB. We can probably get it down to 300 kilobytes or less, but it means prover time. It takes longer to prove the thing. The benefit of this Stark proof is that it is post-quantum safe. It basically just relies on hashes. The
Hmm.
Snark approach, which is a Graph 16 or Plonk, their proof sizes are roughly constant. So it's going to be like maybe like 1 kilo. I can't remember Graph 16, but like 1 kilobyte or maybe even less for Graph 16. Uh, the annoyance with Graph 16 in particular is that it is circuit specific, meaning you're going to need to do um, this thing called a trusted setup per circuit. So you probably just don't want to use it. But Succinct probably has a Plonk proving system somewhere. And those proof sizes are a bit larger than Graph 16, but you can think of them as also roughly constant. Uh, the disadvantage of this is just that it's not post-quantum. Um, I think it's the Gnark-based Plonk one. I can't remember the proof sizes for Succinct, but yeah, the main disadvantage there is that it's not post-quantum. Uh, I don't know. Does that
Yeah,
answer?
so yeah, I think this is what mostly confirms what I understood from the documentations. Yeah, I just wanted to like know for sure that I understand correctly, and I assume that for like the future plans, like for Lean Ethereum, I guess the execution proofs those would be quantum secure starts, right?
Mhm. Right. So
Ye-
the plan is for them to be 300 kilobytes initially, and then we're going to go down to 128 kilobytes. And then that should be enough for the networking layer to handle.
All right. Yeah, but for my use case, because basically these index tables, I mean this index table proofs if like every I don't know 256 blocks we would generate a new table merge round. So roughly like even if someone is willing to generate a new proof for like as frequently as it makes sense, that would be like one new proof per hour or something. So for someone uh, like who, for some client, it's totally acceptable to just download even a several hundred kilobyte Stark from the prover like every hour if there's a new proof. So yeah, I think for my use case probably I can live with even like hundreds of kilobytes or 1 MB proofs, and they don't necessarily have to go on chain. But if I want to do something on chain, then I would have to. I mean, for some reason, I would want to verify a proof on chain. That would have to be a snark, right? So Starks are
Mhm.
not possible to verify on chain. That would be too expensive, right?
Yeah, currently it's pretty expensive, but it's likely that if everyone moves to post-quantum, we're gonna have to change something to make it not as expensive. I don't know what the cost is right now. I believe Starkware probably does it currently, but I don't know how much they pay for their stock proof.
Well, but I think by the way, I also do have this idea that yeah, maybe I also will show you this because now that we are talking, this might be interesting for me. Wait, did I open new ones? Not what I wanted. Okay, yeah. Anyways, this is what I needed. So yeah, this is just this drawing that I have like for one of my talks. So this is something the way I kind of like imagined. So uh, this is how maybe transaction could work in the future. So Vitalik already like wrote in his initial account abstraction EIP draft that certain pre-checks like authorization, signatures, witnesses, those could be uh, proven with ZK proofs before the transaction reaches like the mempool. So this is something like, for example, if we add witnesses to transactions, then the provers could create transaction batches, and basically the witnesses wouldn't have to go uh, into the chain, and also additional ZK proofs could be like recursively mashed into one proof or a few proofs. So yeah, maybe it would be possible in the future to just so I somehow assume that even for like post-quantum signatures, so those would be bigger than elliptical signatures. Probably we would do something like this, and in the end we would uh, like put ZK proofs like in the input of the uh, block building too. So yeah, maybe then putting extra proofs. So what I want to get at is that maybe if we can just verify uh, like one or a few Starks per block, then basically we can verify as many as we want, as long as some provers are capable of doing recursive proofs. So do you think like this is realistic?
I think some of it is a bit TBD. Um, so I can't say for certain right now. The one question I do have is I don't understand what's happening with the first prover column. So they get multiple transactions with witnesses, and these witnesses prove that the transaction is valid, or yeah, I guess.
Well, yeah, and so this yeah, I just really quickly jumped into this without context, but what I wanted to prove with this drawing is that uh, witnesses like if we add witnesses to transactions that are basically so verifying the witness has basically one bit of output, like is the witness correct or no, it's not true because we also have to add what the witness proves. But basically if we have a large witness of like a state read, then then we can verify that witness off chain and the witness doesn't have to go to the chain. So that's what I wanted to prove here. And so the reason I wanted this is that, yeah, I also, this is another drawing where, this is just the crazy idea of mine that with the new log index, but this is not something we should get a conclusion on now. It's just the way I imagine a possible future that maybe we could also use the log index for like contract logic, and I think it would have some advantages. One of them is that it's according to my estimates, about 100 times cheaper to add an entry to the log index than to the state tree. So yeah, so maybe for some applications this would be viable. But the thing is that for the log index, the witness size is not logarithmic but log squared. So yeah, putting the putting log index witnesses on chain uh, is would be probably expensive. But maybe if we can just do this, that we take these witnesses, and I mean, like this a log index witness can be something like 50 or 100 kilobytes, so like kind of big. But if we just prove the ZK prove the verification of these witnesses, then maybe they could be also proven on chain. So yeah, this is
Mhm.
something that maybe yeah we can discuss at a later point, but this is just my latest idea of a future use case for the log index.
Mhm.
It's not something that I need now for the current use case. I'm just thinking about uh, that once we can afford to have uh, one Stark or a few Starks that in a block, then we can have basically as many Starks and witnesses in a block as we want, and
Mhm.
it will have a cost prover cost, but it will not have an extra on-chain cost. So that's my assumption. Do
Right.
you think
Yeah, that makes
this
sense.
can be true?
I think it can be true. I probably need to think a bit more before I say anything like actually
Yeah, yeah.
concrete
All right.
in case I'm missing some details here.
Yeah, yeah.
Uh,
Anyway, this is just something I wanted to quickly show. But anyways, if we know, yeah, we can just first focus on finding a suitable uh, proof system to just prove the table merging. So that's the highest priority. And so yeah, this is the link, and yeah, I will definitely check this out. And yeah, I think I know most of what I wanted to know. I have my answer. Actually, there's one more thing, as one more thing, which will probably be a simpler one. So, I was thinking about the hash function because so there's the hash function I use for tree hashing the tables, because these tables, generating them and verifying them, the cost of it is will mostly be hashing cost. And it would be nice to have a hash function that's reasonably efficient on a CPU. So like the table generation is also efficient, but also it's reasonably efficient for the for the ZK proofs. Someone suggested Poseidon 2, which I never used, but I don't know, or maybe if you have a suggestion for hash function, that would also be useful.
I would probably just start off with Ketchak, just because each ZK VM has um, like accelerators for things like Ketchak. Because when you prove an Ethereum block,
Hmm.
you potentially do a bunch of Ketchaks already. So I'd probably start with Ketchak and see what the worst cases are, before like going to something a bit like Poseidon, which is I guess less uh it's less I guess Lindy, or like Ketchak is pretty it's pretty a safe choice if you put it into like the consensus algorithm or in Ethereum at the moment. Um so I'd probably start with that and see what the worst cases are, and then if it's like too bad, then switch to something like Poseidon.
Okay, so Keccak might be reasonable in a ZK VM, you say. Okay.
It
Also, by the
definitely
way,
is reasonable. Yeah.
so right now I started using actually not so Keccak is SHA-3, but I started using SHA-2, which is for CPU it's like 3-4 times faster. So uh, is it also efficient on ZK VM, or Keccak is better?
I think it depends on how they've accelerated it, but usually they have SHA-2 accelerators as well.
Okay,
Uh,
so SHA-2 or SHA-3 might be a good choice to start with.
right, but you need to sort of use the accelerator uh, version of
Okay,
it, and
and what yeah, so yeah, obviously I don't have to prove the execution trace of like the dump implementation of the hash function. But
Mhm.
so how do these accelerators work? If I read this link, is in this framework, is there something for hash acceleration included?
In that link in particular, no, but roughly how they work is that you have like a particular circuit for Ketchak. So you implement Ketchak as a circuit.
Mhm.
And whenever the Rust program calls Ketchak, instead of calling your normal Ketchak dependency, you have a particular mechanism for calling this circuit instead. So the naive way is to prove like the execution, all the naive dump of like Ketchuk, which is like a bunch of RISC-V instructions. But the smart way is to call this accelerator, just like how CPUs have SHA-2 accelerators, for example, or AES accelerators. You just
Mhm.
need to know how to call it. And at the moment, each ZKVM has a different calling mechanism, but we've just standardized it. So they should be implementing the standardization soon. With the standardization, you basically just need to call a C header and then you're done. Um,
Mhm.
but and send you. I don't know if that makes sense. Let me know. Mm, mm. Can you hear me? Oh, one sec.
Yes, yes. Okay, I can hear you.
Yeah, yeah. So yeah, basically you just need to know how to access those accelerators. Um, I can probably talk to you about it offline for when you do get to it. But the ZKVMs usually provide a library that does all of the that does the access in itself. So you just call it like a regular library, and it won't do the naive thing. It will do the smart thing. But I can definitely talk to you about it offline.
Okay. Yeah, so yeah, we'll definitely need some pointers to yeah, implement this logic in a provable way. But okay, so for now, the important thing is that so this should be possible basically. Yeah, so all those
Mhm.
things that I need is yeah, so I do need recursive proofs and I do need hash acceleration. And yeah, that's pretty much
Mhm.
what I need.
Yeah. But you can do it in two separate steps, right? Like the recursive proof is like a separate program you can think of that just does the merging of proofs. Whereas you have your core logic that just does this table indexing. So it's like two
Wait,
different programs.
so you saying that I shouldn't mix these two logics together?
Yeah, I think it might be easier to separate it, as in you have your core logic, and then you have a thing that takes in, let's say, two proofs and just merges them together. So all it does is just proof merging.
I see. So so like I would have like two verifier functions, and one of them would just have these Merkle proofs as or
Right,
input, this index anti-Merkle proofs, and the other one would just have the recursive proofs as input.
right, right, exactly.
And uh-huh. Okay, okay. That maybe yeah simplifies things a bit. Uh, but still, like if I merge together ZK proofs like recursively, I still need to somehow access the public part of those proofs so that I know what content I'm merging together. So, but I
Right,
guess that should be possible.
right, right. Yeah, you just make it a public input and it should come with the proof. You can think of it as.
Yeah, well, I pretty much how I imagined it anyway. So yeah, this is so yeah, this would be the public input, either full table chains or partially proven tables. And yeah, so basically I would have one function that takes two of these, and somehow we also assume that the proof part would be recursively verified. But yeah, so what I need to care about is merging two of these together,
Hmm.
right?
Right, exactly.
Okay. And in the other case, yeah, generating this from like the Merkle tree proofs. So yeah, okay. I will read up on the links you sent, and yeah, let's continue this offline. But yeah, this was really useful, and I think we're already past 1 hour. So yeah,
Hmm. Yeah,
okay,
cool. Yeah, thanks.
yeah, it was really useful. So yeah, thank you very much.
Mhm.
Okay,
No worries. All right. See you, Joel. Thank you.
okay, thank you. See you. Bye bye.